Let's talk about 30, 60, 90 triangles and 45, 45, 90 triangles. These two triangles have special properties that allow us to solve for the exact side lengths a little bit more easily than other triangles. But first, let's do a quick Algebra 1 review of how to rationalize a denominator. Rationalizing the denominator means to remove the radical from the denominator. It's considered improper to have a radical on the bottom of a fraction. So to get rid of that radical, we multiply both the numerator and the denominator by that radical. So I'm going to multiply this fraction by square root of 2 over square root of 2. So on top, I just have 3 times the square root of 2. And on bottom, I have the square root of 2 times the square root of 2. Well, the square root of 2 times the square root of 2, since those are both square roots, I can combine the numbers under the radical, and that would become the square root of 4, because 2 times 2 is 4. And the square root of 4 is 2. So on the bottom of this fraction, I would have 2, but on the top, I can't do anything to 3 times square root 2. Those aren't like terms, so I just leave it as 3 root 2. And on the bottom, I have 2. So this is the rationalized version of the question that we were given. Let's try another one. Again, our goal is to get rid of the radical in the denominator of this fraction. And in order to do that, we're going to multiply both the top and the bottom by that radical. So on the top, I now just have 11 times the square root of 5, and on the bottom, I have the square root of 5 times the square root of 5. Since both of those are square roots, I can multiply the numbers under the radical together and get 25. And the square root of 25 is 5. So the answer here would be 11 root 5 over 5. Let's see one that has an extra step in it. We're going to start out the same way though. Our goal is to rationalize this denominator, and we'll do that by multiplying the numerator and the denominator by the square root of 3. So on top I have 15 root 3, and on bottom I have square root of 3 times the square root of 3. In other words, the square root of 9. And the square root of 9 is 3. So I have 15 root 3 over 3. But this time I can reduce, because 15 on top and 3 on bottom, those are both divisible by 3. So I can reduce this answer to 5 square root of 3. And let's just try one more. If I need to rationalize this denominator, then I need to multiply both the numerator and the denominator by the square root of 7. So on top, I have 3 root 2 times root 7, and on bottom I have root 7 times root 7. This time in my numerator, I do have 2 radicals that I can multiply together, so I get 3 root 14. And on the bottom, I have square root of 7 times the square root of 7, in other words, the square root of 49. And the square root of 49 is 7. And this is your answer. This one is not reducible because 3 and 7 are not both divisible by the same thing other than 1. And remember that you can't reduce the 14 and the 7 because the 14 is under a radical, so it's basically trapped. You can't reduce these because they're not like terms. We're going to need to be able to rationalize denominators for some of the problems that we're doing today because our problems involve proportions that incorporate radicals. We have 2 special right triangles that we're going to discuss. We have 45, 45, 90 triangles and 30, 60, 90 triangles. They're so called because of their angle measures. A 45, 45, 90 triangle has degree measures of 45 degrees, 45 degrees, and 90 degrees. And if you have a triangle with these degree measures, then the side lengths are in this proportion every time. Since we have 2 angles that measure the same, we must have 2 sides that measure the same. In other words, this is an isosceles triangle. So the 2 legs are in a ratio of 1 to 1. And the square root of 2 is what we have for the hypotenuse. You can actually see that by doing the Pythagorean theorem, that you would do 1 squared plus 1 squared equals x squared. So that would be 1 plus 1 equals x squared. So that's 2 equals x squared. So x must equal the square root of 2. So that's where we're getting this square root of 2 from. So we can use this proportion to solve any 45, 45, 90 triangle. And we have a similar idea for our 30, 60, 90 triangles, which of course have degree measures of 30 degrees, 60 degrees, and 90 degrees. For this kind of a triangle, we do have 2 different lengths for our legs. It's not isosceles like the 45, 45, 90 triangle. So we have 3 different numbers in our proportion, and they relate to the different sides of the triangle. For every 30, 60, 90 triangle, there is a short leg, a long leg, and a hypotenuse. The short leg is the leg that is across from the 30-degree angle, and the long leg is the one that's across from the 60-degree angle. And of course the hypotenuse is across from the 90-degree angle. So we can use this proportion to solve any 30, 60, 90 triangle. Let's take a look at a few examples. The first thing you need to do is identify which kind of special triangle you're working with. In this case, it's a 45, 45, 90 triangle. And the ratios for a 45, 45, 90 triangle are 1, 1, and square root of 2. And that's for the leg and the hypotenuse. So I'm just going to write this as a proportion, filling in the legs and the hypotenuse from my diagram. So one of the legs is 3, one of the legs is x, and the hypotenuse is y. So now I need to take two ratios from this proportion and solve for one of the variables. So if I wanted to solve for x, for example, I can just take the first two ratios and cross multiply and solve that. 1 times x is x, 3 times 1 is 1, so x equals 3. And actually we really didn't need to do the work on that, right? Because since this is a 45, 45, 90 triangle, it must be isosceles, which means these two legs had to be the same length. So you really don't have to show this proportion in this work. You should just know that x equals 3. But let's see what we get for y. I'm going to take the 1/3 ratio, the complete ratio, and set it equal to the square root of 2 over y ratio. Cross multiply and solve that, and I end up with y equals 3 times the square root of 2. I expect you to give me radical answers in this lesson, not decimals. That's kind of the whole point of 30, 60, 90, and 45, 45, 90 triangles, is that we don't have to provide decimals. Instead, we can provide radicals, and those are exact answers instead of approximations. Let's try another one. This time we have a 30, 60, 90 triangle, and the ratios for that are 1, square root of 3, and 2. And those correspond to the short leg, the long leg, and the hypotenuse. So let's fill out this proportion with the numbers I see on my diagram. 1 is for the short leg is 10. Square root of 3 is for the long leg, and the long leg is x. And 2 is for the hypotenuse, which is y. So now I'm just going to take two ratios at a time to solve for each of these variables. First I'll say 1 over 10 equals the square root of 3 over x, cross multiply and solve, and I see that x equals 10 root 3. Then I'll take 1 over 10 again, but this time I'll set it equal to 2 over y. Cross multiply, and I get that y equals 20. And that's all there is to it. So let's try another one. This time we have another 45, 45, 90 triangle. The ratios for that are 1, 1, and square root of 2 for the leg, and the hypotenuse. So filling in the leg, and the hypotenuse, let's solve. Well, again, I don't really need to set up a proportion and solve for x. I can just say that x equals the square root of 5, but if you wanted to, you could certainly use this proportion, cross multiply, and again, you get the answer of square root of 5. The only thing that you really need to show work on for this one is solving for y. So I'm going to take the 1 over square root of 5 and set it equal to square root of 2 over y. When I cross multiply and solve, I get the square root of 2 times the square root of 5. Since those are both radicals, I can multiply the numbers under the radicals and get an answer of the square root of 10. Let's try another 30, 60, 90 triangle. The ratios are 1, square root of 3, and 2. That's for the short leg, the long leg, and the hypotenuse. So let's fill in our numbers. The short leg is x, the long leg is 8, and the hypotenuse is y. So taking this one pair at a time to solve for each variable, I'll say 1 over x equals the square root of 3 over 8, cross multiply, and I have to divide by the square root of 3 this time, so I get 8 over the square root of 3. But as we discussed in the warm-up, that's improper. You're not allowed to leave a radical in the denominator of a fraction, so we must rationalize. In order to rationalize, I multiply the numerator and the denominator by the radical. So I have 8 times the square root of 3 on top, and the square root of 3 times the square root of 3 on the bottom. Well, the square root of 3 times the square root of 3 is just the square root of 9, and that's 3. So my answer here, when I fully simplify, is 8 root 3 over 3. Okay, now let's solve for y. So I'm going to take that square root of 3 over 8 complete ratio and set it equal to 2 over y. Cross multiply, and again I'm going to have to divide by the square root of 3. So I have 16 over the square root of 3, but I need to rationalize it by multiplying the numerator and the denominator by the square root of 3. So my answer for y would be 16 root 3 over 3. So far, both of the 45, 45, 90 triangles that we've looked at, we've known one of the legs, so we didn't have to do a whole lot of work to figure out the other leg. The legs have to match. But this time I don't know either of the legs, I only know the hypotenuse. So let's set up our proportion, 1, 1, square root of 2 for leg, leg, and hypotenuse. The legs are x and y, and the hypotenuse is 7. So really I only need to set up one proportion and solve for either x or y, and whatever I get is going to be the answer for the other one. So let's take a look. If I do y, for example, I can say 1 over y equals the square root of 2 over 7. Cross multiply, and again we're going to have to divide by a radical, so I end up with y equals 7 over the square root of 2. But I can't leave it like that because that's a radical in the denominator, so I'll rationalize by multiplying both the numerator and the denominator by the square root of 2. So my answer is 7 root 2 over 2. And you could show all that work again if you want to for x, but since x and y are the legs of a 45, 45, 90 triangle, they must be equal to each other, so since y was 7 root 2 over 2, x must be 7 root 2 over 2 as well. Alright, let's give one more try. We have a 30, 60, 90 triangle here, so my ratios are 1, square root of 3, and 2 for the short leg, the long leg, and the hypotenuse. The short leg is y, the long leg is x, and the hypotenuse is 2 root 3. So if I wanted to solve for x, I would need to take the square root of 3 over x ratio and set it equal to the complete ratio, which is 2 over 2 root 3. So let's cross multiply and solve. I've got x times 2, and the square root of 3 times 2 times the square root of 3. Well, I notice that there's 2's on both sides. I could divide both sides by 2 and just have x equals the square root of 3 times the square root of 3. And the square root of 3 times the square root of 3 is really just the square root of 9, and the square root of 9 is 3. So x must be 3 inches. Now let's solve for y. So I'll use my 1 over y ratio and set it equal to the complete ratio of 2 over 2 root 3. Cross multiply and divide both sides by 2, and I find out that y equals the square root of 3. And that's the basics of what you need to know about using special right triangles to solve for exact side lengths. In the next video, we're going to discuss how to use special right triangles to solve real-world problems.